Imagine stepping into a bustling factory, where these gleaming strips of steel are just flying by looking, well, perfect.
Hmm.
But what if I told you that in high-precision manufacturing, especially with these kinds of materials, appearances can be incredibly deceiving?
They really can. What looks perfectly flat might actually be hiding some serious issues.
Exactly. Hidden flaws, poised to cause significant costs, big headaches down the line.
Yeah, absolutely.
Welcome, everyone, to a deep dive into precisely this challenge and what sounds like a really revolutionary solution from IMS Messsysteme GmbH.
That's right.
Today, we're unpacking their new magnetic strip flatness measurement system. Our mission really is to understand the ingenious mechanics behind this novel technology.
And explore the benefits, too, the real-world impact.
Yes, explore the profound benefits it brings to industrial production. We're aiming for those clear, concise insights, those aha moments
Mhm.
that help you understand what's truly important without getting, bogged down in jargon.
It's a fascinating problem to tackle because flatness itself, it sounds simple, but it's actually far more complex than it first appears,
Especially under stress, you mean?
especially under stress, yeah. What seems perfectly aligned to the eye or even to conventional optical sensors can hide these critical, costly issues.
Okay, so let's peel back that first layer then. Why is flat not always truly flat when we talk about steel strips? Fundamentally, what does a truly flat strip need?
Right. At its most basic level, for perfect flatness, all the longitudinal fibers within that strip, you can imagine them like countless tiny parallel threads running its whole length. They must have precisely the same length.
Okay, same length, makes sense.
If there's any difference, even a microscopic one, the moment that strip isn't under tension anymore, those length discrepancies, they just show up as visible waves.
So the waves are the symptom of uneven lengths, like a guitar string analogy you mentioned before we started.
Kind of, yeah. Think of it like a perfectly tuned string versus one that's slightly out of whack internally. Once you release the tension, the out of whack part becomes obvious.
And these issues, these uneven lengths, they don't just happen randomly, do they? Where do they usually come from?
Most often, they arise during the rolling process itself. That's where the material is shaped and formed under immense pressure.
Makes sense.
But it's not just the rollers. Other components in the plant, like the coiler at the very end of the line where the strip gets wound up, they can also introduce or even worsen these fiber length differences. It's a whole system thing.
A complex interplay. Okay, so here's where it gets really interesting, and I think where the big problem lies for manufacturers.
Hmm.
For years, traditional optical measurement systems, things like Lascon, Toplan, or even IMS's own standard camera cluster system, the CCS, they've been great,
Right.
right? But only under certain conditions.
Exactly. They work really well when a strip is untensioned. They can directly see and measure those waves we talked about, simple geometry, basically.
But there's a huge catch, a critical blind spot.
There is. And this is the absolute crux of the challenge. When that steel strip is put under high tension, which it often is during production, think rolling processing lines, something powerful happens.
An illusion.
Pretty much, yeah, an illusion. The material undergoes elastic stretching, and this stretching effectively masks those real underlying plastic length differences in the fibers.
So it looks flat, even when it's not truly flat internally.
Precisely. It might appear optically perfectly flat and smooth, but the moment you release that tension, bang, it would spring back into waves.
Wow.
And this is exactly where traditional optical systems just hit their limit, an absolute wall. They simply cannot see the true hidden unflatness when the strip is under high tension.
So if the optical methods were basically blindfolded in these high-tension situations, how did manufacturers even attempt to spot these hidden flaws before? What was the workaround, and what were its problems?
Well, previously, the only real way to get a sense of the true unflatness under high tension was indirect. You'd measure the strip tension distribution across its width.
So measuring forces, not shape.
Exactly. It's not an optical measurement of the geometry at all. It's an inference based on how the force is spread out. If one area is secretly longer, it might carry slightly less tension.
But that sounds indirect,
Mm-hmm.
and probably not super precise.
It has its own drawbacks, yes, especially for consistent quality control, and it doesn't give you that direct geometric picture.
And speaking of quality control, beyond this hidden flatness problem under tension, the traditional ways of checking had other big issues too, right? Especially with these massive coils of steel.
Oh, absolutely. The conventional approach often involved manual quality control, really manual, like cutting physical samples from the strip.
Cutting samples off a moving line. Or at the end?
Usually at the very end of a production run, maybe the start and end of a coil, then someone would take those samples and meticulously measure them offline.
Okay, I can already see the problems.
Right. First, it's sporadic. You get maybe 1 or 2 snapshots for an entire, potentially huge coil, and often that's just not representative.
Especially, you mentioned, with welded strips.
Exactly. Imagine a long strip made by welding several smaller coils together. Each section could have totally different flatness characteristics. A sample from the very end tells you almost nothing about the middle or the beginning.
It's like judging the health of a whole forest by looking at one leaf, like you said earlier.
Precisely. It's slow, it's labor-intensive, it's imprecise, and it's prone to missing widespread or intermittent issues completely. Not ideal for modern production.
Definitely not.
Yeah.
Okay, so problem clearly defined. Hidden flaws under tension, plus slow, spotty manual checks. Which brings us finally to the IMS breakthrough.
Yes, the new magnetic system.
This is the system designed to overcome all these limitations. How does it actually do that? What's the core idea, the innovation?
The core innovation is, I think, incredibly elegant. It centers around an electromagnetic deflection unit.
Okay, electromagnetic deflection, what does that mean?
It means the system uses an electromagnet to apply a very precise, very controlled force perpendicular to the direction the strip is running. Sideways, essentially.
It pushes the strip sideways momentarily.
Sort of, yeah. It creates a measurable bend or deflection. The German term they use is Durchbiegung in the strip as it passes through.
Whoa. Okay, so the system is actively, but momentarily, bending the fast-moving steel strip. That sounds potentially risky, but fascinating.
It does sound it, but it's done very carefully, and that bend is the key.
How does that bend reveal the hidden truth about flatness that the tension was masking? What's the principle?
That's the really clever bit. The amount of that deflection, how much it bends locally, is directly proportional to the local strip tension.
Oh, okay.
Remember those longitudinal fibers we talked about, the ones with potentially different lengths?
Yeah, the core issue.
If one fiber is secretly longer than its neighbor, even though they both look flat under the mainline tension, that longer fiber is actually under slightly less internal tension. So when this external magnetic force is applied,
it will bend more easily.
Exactly. It deflects more under that same applied force. This action momentarily overcomes the masking effect of the overall high tension. It effectively unmasks the true length differences, the true unflatness.
That's the aha moment. The bend acts like a lie detector for the material's hidden stresses.
That's a great way to put it, a lie detector, yeah. You create a temporary, controlled distortion to expose the underlying reality.
Brilliant. So you induce this telltale bend, and then you just need to measure that bend very accurately.
Precisely. That deflection is then measured with extremely high precision using triangulation. And they use IMS's established camera cluster system, the CCS, to do that measurement.
Okay, so leveraging their existing strength in optical measurement.
Right. Richard Rak, who's the CEO of IMS Messsysteme GmbH, he put it nicely. He said, "Our new system overcomes this restriction," meaning the limitation of optical systems under tension. Through an electromagnetic deflection perpendicular to the strip's running direction, we generate a defined deflection of the strip. This is then measured with high precision using triangulation with our CCS system.
That quote sums it up perfectly. A smart physical nudge combined with advanced optical measurement.
Exactly. It's a blend of physics and precision optics.
Let's dig just a bit deeper into the engineering, because applying force to potentially sensitive material running at speed sounds tricky. How does this electromagnetic deflection device work without, say, damaging the strip? That seems like a really delicate balance.
It is a very delicate balance, and it speaks to some clever design. The device uses an electromagnet, obviously, to apply that perpendicular force, but the key is how that magnetic field is shaped. The field geometry is optimized to ensure a constant, uniform deflection force right across the entire width of the strip. No hot spots.
Okay, uniform force. What about preventing damage? Like permanent bending?
Right. That's critical. It's engineered to create sufficiently large bending radii during that momentary deflection. Think of a gentle curve, not a sharp kink.
Ah, so it avoids stressing the material too much locally.
Exactly. This prevents any plastic deformation that's the permanent, irreversible damage. The goal is purely to measure the elastic response, not to alter the product in any way.
Okay, that makes sense. And you said momentary deflection, so it's not bending the strip continuously.
That's right. It's intermittent. The measurement isn't a constant bend. The normally tensioned strip running straight without the magnetic force applied acts as the 0 point, the reference.
Got it.
Then the magnet is switched on and off. But not just flicked on and off abruptly that would cause vibrations. It switched along carefully controlled ramps.
Like dimming a light up and down.
Sort of, yeah. A smooth power up and power down. This minimizes any vibrations or unwanted disturbances in the strip. And with each of these magnetic pulses, the CCS system captures a precise flatness cross profile of the material.
So pulse, measure, capturing snapshots of the flatness across the width.
Exactly. This intermittent pulsing allows for a dynamic and highly precise assessment across the entire length of the strip as it runs through.
And the sensor tech measuring this, the CCS, you said it's an extension of what IMS already does well. Can you remind us how that camera cluster system actually works to get such high precision measurements?
Sure. Yeah, this magnetic system is built as an extension onto their proven CCS flatness technology. The core principle for measuring the strip's surface height, whether it's waves on an untensioned strip or this induced deflection, is optical triangulation.
Triangulation, like surveyors use.
Similar principle. Basically, a laser unit projects multiple sharp lines across the material's surface. Then a second unit, positioned at an angle, houses an array of cameras.
An array, not just one camera.
No, a whole cluster. And these cameras capture the exact position where those laser lines hit the surface. Because the cameras are viewing the lines from an angle, any change in the height of the surface causes the lines to appear shifted in the camera's view.
And based on that shift in the known angle.
The system can precisely calculate the material's height variations across the strip. Simple geometry, but requires very precise components.
What makes the IMS camera cluster system particularly good at this? Why is it so accurate?
Two main things, really. First, using a large array of small adjacent cameras, the cluster allows for exceptionally high resolution. We're talking 5 millimeters spacing in the cross-direction measurement points.
That's dense coverage.
Very dense. And the height resolution is incredible, down to 5 micrometers, 5/1000ths of a millimeter. This setup also allows for a very high measurement frequency, so you can capture data very rapidly, even on fast-moving lines.
And the second thing?
The second advantage is the viewing angle. The cameras look at the laser lines from a nearly perpendicular angle relative to the strip's surface.
Why is that good?
It creates really favorable optical conditions. It makes the system much less sensitive to interference from things like surface reflections, stray ambient light, or variations in the material's surface finish, like whether it's shiny or dull. It's just inherently more robust.
Robust, super precise. And versatile too, you mentioned.
Exactly. Because it's built on the CCS platform, a system equipped with this electromagnetic deflection unit can actually operate in 2 modes.
Oh, okay.
It can function as a classic CCS, directly measuring waves when the strip tension is low, or when the tension is high, you activate the magnetic deflection and it measures the induced bend.
So it covers both scenarios.
Yes. It offers a comprehensive, all-in-one solution that adapts seamlessly to different production conditions. Very flexible.
Okay, this is painting a really clear picture. Let's tie it all together now. We understand the problem. We see the cleverness of the solution. What does this actually mean for, the people involved, whether you're a producer making the steel, a customer buying it, or even just us, interested in cutting-edge industrial tech? How does this breakthrough really transform production? Let's talk benefits.
The impact is substantial, and it hits on several fronts. Let's start with quality advantages.
Okay.
We've mentioned the precision, that 5 micrometer height resolution. This allows for an incredibly precise evaluation of even very subtle flatness defects that might have been missed before.
Leading to a better product, obviously.
Yes, but also, crucially, it provides quantitative reproducibility of results. The measurements are consistent, they're reliable, machine to machine, day to day. This ensures consistent, verifiable quality assurance throughout the entire production process, not just spot checks.
And you mentioned earlier, this data isn't just for internal use.
Absolutely not. This detailed, objective data can serve as documented proof for customers. Think certificates of quality. It demonstrates unwavering adherence to potentially very stringent quality standards.
Builds trust, reduces arguments later on.
Exactly. It can significantly reduce disputes or problems further down the supply chain when the material gets used. Transparency is key.
Makes sense. Okay, quality is clear. What about process advantages? How does it make the actual manufacturing run smoother?
Several ways. A big one is the non-contact operation. We touched on it, but it's worth stressing.
Using lasers, not touching the strip.
Right. Operating via line lasers means 0 physical contact. This completely prevents any risk of scratching or damaging sensitive material surfaces, which is crucial for many applications like automotive body panels or high-grade appliances.
Good point. What about fitting it into a factory?
The system has a relatively compact design. This allows for pretty straightforward integration into existing production lines without needing massive overhauls or huge amounts of space. It integrates physically and also into the plant's control systems.
And the real-time aspect.
That's huge.
Yeah.
Because it measures continuously during ongoing production, it provides these high-resolution flatness profiles in real time. Operators get immediate insights into exactly what's happening with the material's flatness right now.
No more waiting until the end of the coil and cutting a sample.
Precisely. Instant feedback.
And what about the people, the operators and engineers? Does it make their lives easier?
Definitely. The automated data acquisition and evaluation capabilities are a real game changer for them.
How so?
It significantly reduces the manual workload. No more sample cutting, offline measuring, manually logging data, and it minimizes the sources of human error that inevitably creep into those manual processes.
So smarter, faster, and more reliable operations overall.
That's the goal. It frees up personnel to focus on optimizing the process, not just checking it.
Which leads us inevitably to the bottom line. The cost advantages must be pretty compelling here.
They really are. It ties directly back to catching problems early. The system directly contributes to reducing scrap.
Because you spot bad material sooner.
Exactly. You detect faulty products almost immediately. This allows for corrective measures to be taken before you've produced kilometers of substandard strip. Think of the savings in material, energy, and time. Massive.
And less rework too, I assume.
Yes, minimizing rework is another big cost saving. Fixing flatness issues after the fact, if it's even possible, is expensive and time-consuming. Preventing them is far better.
Now, you mentioned something really interesting earlier, regulative implementation. What did you mean by that?
Ah, yes. This is perhaps one of the most powerful aspects. Because the system provides such a detailed, real-time flatness profile, it's not just a passive measurement device.
It can control things.
It can feed information back to and actively control upstream components in the production line, things like the rollers or tension controls.
Wow, so it can tell the rolling mill, hey, adjust slightly here to improve the flatness.
Essentially, yes. It enables closed-loop control. It works proactively to improve flatness in real time, not just report on it after the fact.
So it's not just finding problems. It's actively helping to prevent and fix them on the fly. That's impressive.
It really is. And when you combine all these advantages, reduced scrap, minimized rework, less manual labor, proactive control, documented quality, the result is significant cost savings and a real competitive edge.
Allows companies to hit higher standards more efficiently.
Exactly. Immediate recognition and correction of quality deviations lead to better output, produced more efficiently and sustainably. Richard Rak, the CEO, summed it up again. With our magnetic strip flatness measurement system, we offer a solution that meets both the quality and efficiency requirements of modern production lines. It is flexible, economical, and delivers precise measurement results that form the basis for optimized and sustainable production in process lines.
That's a powerful summary. What a comprehensive look at a truly impactful piece of technology. We've taken quite the deep dive today, haven't we?
We certainly have.
We've seen how IMS Messsysteme GmbH has brought this genuinely revolutionary system to market, tackling a challenge in material production that was, for a long time, kind of hidden in plain sight.
Masked by tension.
Right. From understanding why high tension creates that optical illusion, masking critical flaws, to seeing the really elegant solution of electromagnetic deflection combined with that super precise optical measurement. We've really explored the cutting edge of industrial quality control here.
And it's probably worth just briefly mentioning IMS Messsysteme GmbH isn't some newcomer. They've been around since 1980.
Right, a long history.
Yeah, they've built a global reputation as a leader in measurement systems. They have something like over 4,500 non-contact systems installed worldwide, all focused on optimizing processes and reducing waste. This new system really feels like a continuation of that commitment to innovation.
It definitely does. And, thinking about this clever approach, combining basic physics like electromagnetism with advanced optics to see something that was previously invisible, it raises a broader question, doesn't it? Well, it makes you wonder, what other invisible problems are lurking out there, maybe beneath the surface, across completely different industries? Problems that could potentially be solved if we just found the right way to combine established physical principles with advanced measurement.
Like finding new ways to see beyond just the superficial appearance of things.
Exactly. How can we learn to look past the surface and truly understand the core of a material or a process, or even a system. It's about finding the right lens, maybe even creating one, like IMS did here with magnetism.
That's a really interesting thought to leave things on. What else are we missing just because we're looking at it the wrong way or with the wrong tools?
Precisely. Something for all of you to ponder, perhaps, until our next deep dive.